Okay, so for our standard generic reaction, A and B go to C plus D. Our equilibrium constants is products of reactants raised to their coefficient. There's a pressure version of this as well. You talk about that in 124. We're not going to worry about that a whole lot because we're going to really focus on solution-based stuff in this class. I'm going to go ahead and tell you, because these are concentrations and they're raised to some powers, it could be that we end up with things that should have a unit, right? Some version of molarity or inverse molarity, but K is always unitless. And the reason K is unitless, our equilibrium constant is unitless, is because in reality, all of these are divided by 1 molar. And that's just to get them in their standard state, so relative to standard conditions. This is also the standard conditions business is also why we ignore pure solids, pure liquids, and gases, because they're already in their standard states. Okay. And so this is why we end up with a unitless equilibrium constant, because we divide through by 1 molar. And then you have molar over molar, and everything is, that the units cancel out. All right, so what would happen if we change the direction of the reaction? Right? We said C plus D gave us A plus B. What would happen to K?
A and B would be on top instead.
Yeah, so we would just, the top and bottom flip, we call that inversion. And so we would just invert K, right? Raise that to the negative first power. Right? What if we had multiple reaction steps? What do we do with the Ks? So let's say we have a K1 and a K2, and I want to get a K overall. What sign goes in the middle there?
Plus. Times.
Excellent. Yeah, we multiply those equilibrium constants together when we have an overall reaction. We'll talk a little bit more about multiple steps in a later slide. Okay. So that's the basics. Like I said, there will be some homework problems associated with that, so you have any questions, let me know. So one of the things that affects equilibrium is adding or removing compounds, changing pressure, changing temperature, all these kind of things can shift our equilibrium. And this is all called Le Chatelier's principle, right? How that equilibrium shifts due to outside stressors. And so, what will give us a shift to the reactants? Pick anything.
Removing a product. I mean, removing a reactant.
Yeah. So if we remove a reactant, our equilibrium will shift back towards those reactants to try to replenish some of that, right? And so conversely, a shift to products would be if we remove a product. Okay. Somebody tell me something about an addition.
Say that again, please.
Something about an addition. What if I added a reactant? Which way would it shift?
To the products.
Yeah. If you add more of a reactant, it's going to want to shift to products, get rid of some of that reactant. Same if we add some products, it's going to shift back to reactants. It's going to convert some of those products back to reactants. So for these last two, I'm going to label this next to the last line endothermic. And this last line exothermic. I don't know why I put a big old space there, but that's okay. And so for an endothermic reaction, tell me what happens if I heat it up.
Go into the products.
Yeah. So remember, endothermic means that it uses energy. If we add heat, we're adding extra energy, and so we're going to be able to convert more of our stuff over to products. And so if we add heat, we shift to products for endothermic. And if we remove heat, we shift to the reactants. Exothermic, exactly the opposite, right? It's going to shift to the reactants. If we add heat, it's going to shift to the products if we remove heat. We can think about heat as being a reactant or a product based on whether it's endothermic or exothermic. It's going to be a reactant or a product, right? If it's endothermic, we think about it being a reactant. And if it's exothermic, we think about it being a product. And so then we can use Le Chatelier's principle to think about it that way. I always think about Le Chatelier's principle like a bicycle. And so if you get on a bicycle and let's say you add a reactant, right? I know my camera is probably reversed for you, but I'm going to use my left hand. I'm going to add a reactant, right? I'm going to push my handlebar that way, adding my reactant, and my bicycle goes to the right, right? It goes to the products. If I remove a reactant, my bicycle goes to the left, back towards the reactants. Opposite's true for the products. If I add a product, it's going to shift to the reactants. And if I pull back on a product, if I remove a product, it's going to shift to the products. Right? And so I always think about Le Chatelier like a bicycle. Okay. All right. So there's one other thing that we can talk about. So we talked about, concentrations changing. We talked about temperatures changing. We can also change pressure. Pressure is a little bit trickier. Is there a question?
No.
It's okay. And so if we increase pressure, how do we figure out which direction we're going to shift?
The number of moles on,
Yeah, number of moles of what, Beck?
you mean like of the product? Like added together?
So which
Or what do
phase cares about pressure the most?
Gas.
Gases, yeah. So if we increase pressure, right, we're going to shift to the side with fewer moles of gas. Right? Not fewer moles overall, but it has to be fewer moles of gas. Right? If I have my products have 3 moles of a gas, my reactants have 2 moles of a gas. If I increase pressure, I can try to regain equilibrium by decreasing pressure and shifting to the side with only 2 instead of 3. Right? The vice versa is true. I'll just write it here for completeness sake. If we decrease the pressure, we're going to shift. We're going to try to reach that equilibrium again, try to re-increase that pressure. We're going to shift to the side with more moles of gas. Okay. Another way of thinking about the Le Chatelier principle is thinking about the equilibrium versus this reaction quotient, right? And so the reaction quotient gets the symbol Q, and it is calculated exactly the same way, right? Q for our standard reaction, C moles of C, D moles of D, A moles of A, and B moles of B. And so we could have 3 different options here. Relative to K and Q. Right? The easiest is if K is equal to Q, right? So the difference is that this reaction quotient can be calculated whenever we want, at any point in a reaction. The equilibrium constant, those values have to be equilibrium concentrations. They can't just be, I added all these things together, here's the concentrations. It has to reach equilibrium first. And so if K equals Q, then obviously we must be at equilibrium because the concentrations that we used for Q are the same as the concentrations that we used for K. And so we're at equilibrium. And so if K is larger than Q, which direction are we going to shift? Are we going to shift towards the products or shift towards the reactants?
Product.
Yeah, product. K larger than Q, wait a minute. K larger than Q means that our numerator is too large, and so we need to get rid of some numerator, right? If K is larger than Q. And so if K is larger than Q, we need to get rid of some numerator. Some numerator is some products, and so we're actually going to shift towards the reactants if K is larger than Q.
Oh, yeah, that confused me for a second.
Yeah. What did we decide? I think the reason this is confusing me is because usually it's Q greater than K or Q less than K. So Beck, maybe you were right. If Q is less than K, then we need more products in order to reach equilibrium. So I think you were right.
Okay, yeah, I think I do write it the other way usually.
Yeah. Let's think about this as Q less than K, Q greater than K. Maybe that's easier for us to think about. Okay. And so if Q is less than K, we need more stuff in our numerator, and so we need to shift towards products. If Q is greater than K, we have too much stuff in our numerator. We need to shift away from products, and so that's to the reactants. Now that I've thoroughly confused you. And so the reaction quotient doesn't tie in directly with Le Chatelier's principle. Le Chatelier's principle talks a little bit about changing conditions. But if we know all of our concentrations and then we know what they change to, we can calculate Q and compare it to K and see which direction we need to shift. Okay. All right. So in this semester, we're going to talk mostly about 3 different kinds of equilibrium. We're going to talk about solubility equilibria, precipitation, and all that good stuff. We're going to talk about acid-base equilibria, Ka, Kb, Kw, all that good stuff. And then we're going to talk about complex formation equilibrium. We'll especially do that talking about EDTA titrations and forming metal ion complexes and things like that. So the first of these is solubility product. We call this KSP. For each of the types of equilibria, they have definitions about how we should write those reactions so that we come up with the same form of the equilibrium constant every time we write it. And so KSP, we start with whatever our insoluble salt is. I'm just going to use AgCl as an example. And we put it in equilibrium with its ions in solution. And when we write it like this, K is equal to KSP. Now I could just as easily write it the other way, right? It's the same reaction, it's an equilibrium. But if you write it where the ions are the reactants and the salt is the product, then we don't end up with KSP, we get 1 over KSP, right? And so be sure to write it with the solid salt on the left as a reactant and the ions on the right as products. Okay. This makes it easy because remember solids we ignore from our equilibrium expressions, and so KSP is just equal to the concentration of silver plus times the concentration of Cl minus. When we go to solve for solubility, we can look up our KSP, 1.8 times 10 to the negative 10. I think is AgCl. We'll roll with it even if it's not exactly. Because there's a 1-to-1 ratio, this one's pretty easy. We get an X and an X for silver and chloride. And so we just end up with X squared for our solubility. And so X is the solubility. We can solve for X, square root of that, 1.8 times 10 to the negative 10, square rooted, 1.3 times 10 to the negative 5 molar. So these units just appear, right? We went from KSP, which is unitless, to molar, because remember, when we write these equilibrium concentrations in brackets, really what we're saying is whatever the real concentration is divided by 1 molar. And so when we remove those brackets, we have to put that molar back. Okay. There are some common values for solving KSP problems. We talked about this a little bit in lab, I think. I don't remember exactly where we mentioned it, but I think we talked about it in lab. X squared, right, if it's a 1-to-1 ratio. If you have something like barium hydroxide, right, where it's a 1-to-2 ratio, you'll end up with X and 2X squared, which gives you 4X cubed, right? If it's a 1-to-2 ratio. If it's a 1-to-3 ratio, something like lithium phosphate, I think these were the ones in your review, you end up with 3x cubed times x, which gives you 27x to the 4th. If you have a 2-to-3 ratio, so let's say it's calcium phosphate, you end up with 3x cubed times 2x squared. That's 27 times 4, yeah, that's 108 x to the 5th. Now, if you have a 2-to-2, those are unusual because we would normally just write those as 1-to-1. But you know, mercury is that funny thing where mercury 1 is really Hg2, 2+. We won't worry about it. These are some common ones, right? So if you have a 1-to-1 ratio, it's x squared. A 1-to-2 ratio, 4x cubed. A 1-to-3 or a 3-to-1 ratio, 27x to the 4th. And then a 2-to-3 ratio, 108x to the 5th. There are bigger ratios out there, but these are the common ones. Let me take a moment and step back and say, I like teaching shortcuts. It makes life easier. Like doing this, we didn't have to do an ice table to figure out what K was equal to in terms of X. But because I teach that way, that does not mean you have to solve problems that way. If it makes more sense to you to write out an ice table, and by all means, write out an ice table. Right? Solve it the way that makes sense in your head. Don't solve it the way that I teach it, because that may not be the most logical thing for you. All of our brains work a little differently. And so for me, I remember these 4 versions of KSPs. But if you need to write out a quick ice table and figure it out, by all means, do that. Please do whatever will get you the right answer. And if you get frustrated with me for writing shortcuts, say, can you work this the long way? I'm happy to, really, honestly, truly, anytime. I'm happy to work it the long way. But to me, it's just the way I teach it is a shortcutty kind of method. Okay, that being said, let's move on to this common ion effect. So common ion effect is something that sort of harks back to what we talked about with Le Chatelier, right? And so here you're not adding one of our products or reactants, but you're adding something that carries a similar ion. And so this only works obviously when we have ionic compounds that dissolve in water. And so let's use AgCl for another example. So in equilibrium with Ag plus and Cl minus, okay. So we don't care about solids, and I start with No silver. But let's say that we want to know the solubility of AgCl in a solution that's 0.03 molar silver chloride, sodium chloride. So because we start with some chloride that doesn't come from silver chloride, not quite as much of that silver chloride is going to be able to get over into solution. And so when we add our plus X and our plus X, 0.03 plus X, then when we solve our KSP, 1.8 times 10 to the negative 10 equals 0.03 plus X times X. I'm going to ignore this plus X for now. So I'm going to put him in a box and just solve it that way. 1.8 times 10 to the negative 10 divided by 0.03. X equals 6 times 10 to the negative 9 molar. And so the other one was something times 10 to the negative 5. This is times 10 to the negative 9. So our solubility goes way down. So solubility, let's see, decreased by a factor of 10 to the 4th, right? So that's 10,000 fold, 10,000 times less soluble in a solution that's just 0.03 molar sodium chloride. All right, so back to this ignoring X business. My general rule of thumb is that go ahead and solve it like X doesn't, that plus or minus X doesn't exist. Let me make sure that I'm clear about plus and minus X's. Solve it as though those plus and minus X's don't exist. And then the rule that we're going to use is that it's okay to ignore if X is 1,000 times smaller than the value. Right? So it has to be a pretty small change, you know, so 1,000 is 1/10 of 1%, right? So that's sort of the cutoff. If it's more than that, then we want to go ahead and solve it, quadratic it, whatever. If it's less than that, we are okay ignoring it. And so for this one, X was 6.0 times 10 to the negative 9 molar, and we were talking about 0.03 molar. And when we do that math, 6 times 10 to the negative 9 divided by 0.03, I get 2 times 10 to the negative 7. And so 1,000 times smaller, right? Remember that's 10 to the negative 3. So this is much smaller than that, right? This is 20 million times smaller. And so this X is certainly ignorable. Right? And so if it's 1,000 times smaller than whatever value you're adding or subtracting it from, ignore it, right? If not, do the quadratic. How do you remember your quadratic? Do you have a song? Do you have a mnemonic? What do you have?
I don't really know if I do remember the quadratic.
Excellent.
You mean the quadratic formula?
Yes, sir.
Negative b plus or minus the square root of 4 times a times c all over a, I think.
All over 2a, yeah. So I have a little song that I learned when I was in 10th grade or whatever. Negative b, plus or minus square root, plus or minus square root, b squared minus 4ac, b squared minus 4ac, all over 2a, all over 2a. So quadratic, there you go. For a lot of these really insoluble salts, we will ignore X a whole lot. There are some things, especially in the acid realm, that yes, they're weak acids, but they still dissociate quite a bit. And so in the Ka part of this course, we will probably do a few more quadratics than in the KSP part of this course.
Dr. Davis. So just to clarify, this rule stands for also solving, like you just said Ka. So because in Chem 2 we're taught like 5% dissociation is okay.
I know.
But this is a lot smaller, right?
This is a lot smaller, yeah.
Okay.
So analytical, anal retentive, 5% is way too much. And so we want it to be small. Some places out there say 0.5%, so 10 times smaller than what you learned in 124. I think our textbook goes with this 1,000 rule, and so I'm going to stick with that. All right. So these stepwise formation constants, I told you that we would come back to that. If we have something that reacts in steps, let's say that we're adding on ammonia molecules to a copper ion in solution or something that forms an aqueous copper complex. And they don't all add at once, or they're going to add one by one. And so K1, the first one, is going to, well, let me write out the expression over here. M plus X in equilibrium with Mx, right? That's our first one. And so that K1 is equal to Mx over M times X. Easy enough. K2, so if we were adding the second one on, then I would have Mx2 over Mx times X. And I'll write that out real quick just so that you follow along with what I'm talking about. So this is when we're adding X's on one by one. And we could add on as many X's as we'd like. So N, right, would be Mx to the N, or not to the N, but Mx of N, times N minus 1 on the bottom, times X. And so that maybe we're adding 6 of them, and we don't want to write out every single one of these. Now you know, or at least I told you, that when we add reactions together, we multiply their K values. When we do that, we take it away from K to show that it's not one reaction, but a series of reactions. And it gets the symbol beta. And so there is no beta 1, right? Because beta 1 and K1, you're just adding one thing. But beta 2 is equal to K1 times K2. And it's telling you the overall equilibrium constant for taking a metal and 2 X's and giving you Mx2, right? Even though we know that that's not how it works, you have to add 1 X to M and then add another X to Mx. This beta is wrapping it all together into a single reaction. And so since we have K1 and K2 here, I'm going to write this out. So Mx over M times X times mx2 or mx times x. I need to get some common denominators in here. Let me clean that up. I fudged up a little bit there. Okay. So we need to get some common denominators in here. But you'll notice that we have mx on the top and mx on the bottom. Those cancel out. And then we have mx2 on the top and mx times x on the bottom. Well, x times x is x squared, so we end up with mx2 over m times x squared. And for beta n, again, that's k1 times k2 dot 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 times kn, however many we're going to have. And the way that works out is that you'll have these sort of sequential cancelings, and we just add up our x's on the bottom, and so we end up with mxn on top, m times x to the nth power on the bottom.
I'm sorry, Dr. Davis. What is the point of this? Like, is this just another way to do what we were doing earlier?
So if we're making complexes, so especially when in inorganic, you'll have these metal complexes with things that aren't necessarily ions. And so a common one is ammonia, for example. You put copper ions in a solution with ammonia, and it turns this very deep dark blue color because the positive charge of the ammonia interacts with the lone pair, the positive charge of the copper interacts with the lone pair on the ammonias, and those ammonias are attracted to the copper. They don't form any kind of real chemical bond. They're just, those intermolecular forces are strong, right? And if we want to know how that occurs, well, they add one at a time. They don't all six just jump in at once. Sort of how in organic, you talk about how you have a stepwise mechanism versus a concerted mechanism. Here, we don't have a single reaction because this is happening all over. We could absolutely write, let me do this, m plus 2x is in equilibrium with mx2, right? That would give us this equilibrium constant. And m plus nx in equilibrium with mx to the n. That would give us this equilibrium constant. And these are equilibrium constants. We know that they are, but we use beta instead of k to sort of signify that, hey, I recognize this is not just a single reaction taking place, but a series of reactions.
That makes sense. Thank you.
Sure. Okay. All right. 3 minutes. Do I dare? So fractional precipitation is when we use the fact that things have different KSP values. They will precipitate at different concentrations. To selectively precipitate a single metal. Okay. So I just told you, well, I'll just say a single ion. It doesn't have to be a metal. So if we had AgCl and AgBr, These things are both pretty insoluble. I'm going to look up the real values so that we're not just making numbers up. As much as I love to just make numbers up. Silver chloride is 1.8 times 10 to the negative 10. So I was good there. Silver bromide, 5.0 times 10 to the negative 13. Right? So if I have a solution that has a mixture of Cl and Br minus, right? Cl minus and Br minus, and I put in a drop of silver, which compound is more likely to precipitate, silver chloride or silver bromide?
Silver bromide.
Yeah. So this guy is easier / more likely. Just what's happening? More likely to precipitate. And so in fractional precipitation, you sort of calculate how well can I separate these two things out, right? These KSPs are different by a factor of 1,000. So maybe it's reasonable to think that we could separate these to 1 or even 0.1%, right? I can get rid of 99% of the bromide and leave the chloride behind. This is how they separate out. It's more often done with metals than with negative ions, but it's a way of doing separation of metals in solution. I'll leave you there with the request that take a look at this example. Right? The next couple of slides in your slide deck are an example of fractional precipitation. It's actually just the same slide twice, just I wanted a little extra room for when I write it out. But go ahead and see if you can start working on that before we meet on Friday, and that's where we'll pick up. Okay. Like I said, no lab today. Oh, I'm sorry. I'm going to do it. We don't have a lab today. We're going to do this example. You can hang on an extra 10 minutes. So here we go. We have a solution that's that 0.05 molar calcium 2 plus, 0.03 molar silver plus. And I want to know, can I take 99% of the calcium out without precipitating the silver? These two KSPs are very close together, but the calcium sulfate KSP is a little bit smaller. No, it's a little bit larger than the silver sulfate. And so what is the concentration of calcium going to be when the silver sulfate begins to precipitate? Right. How in the world do we approach a question like this? What's our first way of doing things? So I'm going to use this first slide to talk about just the sort of the procedure, the process of solving a problem like this. And so often things are given in terms of a percentage. And so you're going to use that to your advantage. Right? So use the percentage to determine the desired concentration of the precipitating agent. The precipitating agent in this case is what? What am I precipitating it with? Sulfate. I'm precipitating with sulfate. So I'm going to use that percentage to figure out how much the sulfate concentration is, right? And then we're going to use that concentration to determine the concentration of the second ion. Okay. So let's do some math. 99% of calcium precipitated means that 1% of calcium is left. If I start with 0.05 molar, 1% of that is 0.0005 molar. And that's my calcium ion concentration. So that's 1% of this. Again, it's 1% because that's how much is left after I've precipitated 99%. So then I use my KSP, 2.4 times 10⁻⁵. That's the concentration of calcium, 0.00050, times the concentration of sulfate. And then I find my concentration of sulfate, 2.4 times 10⁻⁵ divided by 5 times 10⁻⁴. And I end up with 0.048 molar. So now I'm going to use that information to see what the to see whether or not silver is precipitating. To figure out whether or not silver is precipitating, I really need to calculate Q. I need to see where it is relative to K, right? And so I know what KSP is, but I don't know what Q is, right? And so Q is equal to my silver concentration squared times my sulfate concentration. Let me just write this SO4 2 minus. So what we're doing is we're seeing whether or not the silver is precipitated. So I'm just using that concentration of silver, 0.030 squared, and this concentration of sulfate, 0.048. I'm going to see what Q is. I got 4.3 times 10⁻⁵. Okay, Q and K, let's compare them. Q is greater than K. Yeah, good chance to review the flub up I made earlier. Q greater than K, that means we have too much product. Too much product means we shift back to reactant. And so if I shift back to reactant, am I keeping silver as an ion or am I putting silver in a solid?
Solid.
Solid, how do we know that?
Because to dissolve, that would be a product, right?
Exactly, when we write our KSP, the solid has to be the reactant, the ions have to be the product. So this is going to shift to reactant, which is the solid. So the straight up answer is no, I can't. Right? I cannot precipitate 99% of silver, 99% of calcium without precipitating silver. Right? In order to be yes, Q would have to be less than K, right? Q would have to be less than K in order for the answer there to be yes. So, first answer is no. The second question though, what's the concentration of calcium when the silver begins to precipitate? In other words, how much of the calcium could we get rid of without precipitating any silver? Okay. And so we use our KSP. So 1.5 times 10 to the negative 5 equals 0.030 squared times the concentration of sulfate. So we answered the first question, answer was no. Now I want to know what's that sulfate concentration that will start silver precipitating, and how much calcium will that concentration of sulfur get rid of? (1.5 times 10 to the negative 5 divided by 0.03 squared is 0.01666666666666666666. Too many sig figs. 0.017. Okay. I'm just going to free up some space here. And so now I'm going to plug everything back into the calcium KSP. 2.4 times 10 to the negative 5 equals the concentration of calcium times 0.017 molar for the sulfate. 2.4 times 10 to the negative 5 divided by 0.017. So this is how much calcium remains before the silver starts to precipitate, or sort of at that moment when the silver starts to precipitate. Right? And so we just need to do a ratio now, right, to figure out what, well, so this actually just asks what's the concentration. Well, there it is. That's the concentration. There's our answer 2. Right? So no, answer 1. The concentration of calcium, answer 2. I'm going to take it one step further and say that I want to know how much of the calcium has been precipitated. 0.0014 divided by 0.05 is 2.8% remain. Right, and so we got rid of 97.2%. So we can do pretty good. We can do pretty good, but we can't do 99%. Right? But we can do 97.2%. Okay. So these problems are a little bit long because you got to kind of go back and forth between what you're looking for and what you have. But this is a very useful technique that's used a lot in chemical industry when you're trying to get rid of a particular ion in a solution. All right. Well, that's where we will call it. Hey, Maddie, go ahead. Ask me a question.
Can you go back to the slide before? I just didn't get the second arrow, the words there. Yes, thank you.
So this lecture I'm recording on my computer, and so this will be up later this afternoon. You can go back and take a look, see. All right, so we will continue our discussion of chapter 6, talking about acids and bases, so shifting gears from KSP to acids and bases on Friday, and we may talk a little bit about chapter 9. So this equilibrium stuff is sort of spread out across a lot of chapters. Chapters 6, 7, 8, 9, and 10 are all equilibrium. And so we finish up chapter 6 and then maybe dip our toes into chapter 9, which is the continuation of acid and base stuff on Friday. Okay? All right. Well, if you do happen to be studying in Milliken and you'd like to come get some socially distanced candy or something, stop by. Have a good afternoon.
Have a great day.
Thank you.
Dr.
Thank you.